In this video, I want to talk you through question 6, part A, of the June 2014 Edexcel FP1 paper. Let's have a quick read of the question. The rectangular hyperbola, which we're just going to denote by h, rather than writing rectangular hyperbola or call it rectangular hyperbola all the time, we're just going to write h for convenience, has the Cartesian equation xy equals c squared. Stop. Two things should be screaming out at you already. What on earth is a rectangular hyperbola, and what on earth is a Cartesian equation? Okay. Now the second one, I would perhaps expect you to have at least heard of it before. But the first one, a rectangular hyperbola, nah. I would not expect you to know what one of those are, and nor would the exam board. Okay, it's beyond the scope of your FP1 course. All you need to know is that it is a graph. Okay, so it's a graph. It's probably going to look something like a rectangle, but you know, it's just a graph. As long as you just think, right, it's just some graph, it's some curve. Okay, you're going to be absolutely fine just thinking that. Second part, what is a Cartesian equation? Well, a Cartesian equation it's something which can be plotted on a Cartesian coordinate. So it's a graph which can be plotted on Cartesian coordinates. What are Cartesian coordinates? Well, you've known them all your life, basically. They're an XY set of coordinates. Okay, so a bit of a cross, bit of up. Okay, you've known those all your life. Named after, it was thought up by the French mathematician and philosopher René Descartes, which is where the cart bit comes in the Cartesian coordinates. Okay, so basically a Cartesian equation, xy equals c squared, just means that you can plot that xy equals c squared on this graph. Okay, on these set of axes. That's all Cartesian coordinates mean. Okay, let's go on. So the point P, which is given by the coordinates ct, c over t, where t has got to be greater than 0, is a general point which lies on our rectangular hyperbola h. And we're asked to show that the equation of the tangent to h at that point P is given by this thing here. Okay, so what have you got to think? Well, what is an equation of a tangent? A tangent is a straight line. Okay, so let's try and visualize this. We've got a rectangular hyperbola. I've got no idea what it looks like, so I'm just going to draw it like that. It could look like anything you like, but, you know, I'm just going to draw it like that. Then we've got a general point P. So here's my general point P. Here's my rectangular hyperbola. This is the graph of my rectangular hyperbola. And here's my general point P. Okay, and it lies on some axis, but I'm not going to bother drawing them in. We've got some general point P which lies on our rectangular hyperbola, and we then need to find the equation of the tangent line, which is at P. Okay, well, a tangent is a straight line. And so therefore, we can, whenever we find the equation of a straight line, okay, we can use our old friend, y minus y1 equals m times x minus x1. Okay, so what do we need? Well, we need a point which lies on this straight line, which we want, so x1, y1. And we also need the gradient of that straight line. Okay, so if we got those two things, then we can use this formula and it will fall out. Okay, so have we been given in the question a point which lies on that tangent line, on that straight line? Yes, we have. The point P lies on it. So we know now that we can use these coordinates. So x1, y1 is just simply our point P, which is ct, c over t. Okay, so x1 is ct, y1 is c over t. Do we know a gradient? No, we don't. We haven't been given a gradient. So what do we need to find? We need to find what the gradient is of that tangent. So in other words, we want to find what that gradient is at that point P. Okay, so the gradient of that hyperbola is at that point P, because that is what a tangent line is. It's representing the gradient at that particular point. So you can see over here, you know, the gradient will change. You can see over here the gradient will be sort of something like that, it'll be negative, like that. Here it's a little less steep. Here it's kind of flattens out. Here again it sort of raises at the end. Here it goes positive down this end. So, you know, a tangent is just a representation of what the gradient is. Well, do we know an expression for the gradient? Well, yes, we do. It's change in y divided by change in x. Okay, so change in x. And we normally give change, okay, in physics you probably come across this. Change is normally abbreviated to the Greek letter delta. So change in y over change in x. Okay. Well, let's have a little bit of a think now. let's consider some general curve like this, okay? And let's consider a small section of that curve and blow this up, okay? So it's going to look something like that, okay? And then let's consider a smaller section of that curve again, okay? So this is this section blown up. Let's consider a smaller section. Okay, well that's going to look something like that. Let's consider a smaller section still. Okay, so let's consider that section. That's going to look something like that. And let's consider that section. That's going to look something like that. So basically what I'm trying to show is that as we consider smaller and smaller sections of curves, they become a straight line. Okay, so the theory goes that if you consider a smaller and smaller section of this curve, okay, let's consider a section of this curve that is so close to zero, the smallest possible size, the smallest possible section of that curve that we can consider before it goes to zero. So in other words, when it's infinitely small, okay, so there is just about some of that curve left before there's nothing left, before it goes to zero length. Okay, and when that happens, we are considering a tiny change. Now let's just think about the Greek letter delta. If it's a big change, okay, we give it the capital Greek letter delta. If it's a small change, we give it the small letter delta, which looks something like that. I think some people draw it like this as well. I tend to draw it like that. And if it's a tiny, infinitely small change, which is the type of change that we want to consider with curves, we give it the normal letter D. Okay, so we represent that as normal letter D. So in other words, we're considering a smallest section of the curve that we possibly can. So it's basically a straight line. Okay, so that we need to consider the smallest section D. So the gradient is given by dy over dx. That's differentiation, isn't it? Okay, I've kind of cheated my way in there and just sort of shown you the intuition rather than showing you the actual formal proof, but that is just differentiation. Okay, so basically if we differentiate a curve, that will give us the gradient at any point. Okay, if we sub in that point into our expression for the gradient, we are going to get the gradient at that point. Okay, so let's differentiate our thing. So we've got our rectangular hyperbola is given, our h is given by the Cartesian coordinates, or Cartesian equation I should say, xy equals c squared. We're told that in the question. So basically if we differentiate this, we're going to get the gradient, which is what we're after, and sub in our point, then we're going to get the gradient at the point which we're after. Okay, so it's not in a form that we can differentiate in the moment, so let's just rearrange it. So let's get the x, so we want y on its own, so let's divide by x, c squared over x. Okay, and that's still not in a form that we can differentiate in, because we need x to some power, not 1 over x. So let's keep the c squared on its own. This is the same as c squared over x is the same as c squared times 1 over x, isn't it? It's just fractions. You can verify that. We just multiply tops together, c squared, this is c squared over 1. Multiply tops together, it's going to end up c squared. Multiply bottoms together, we're going to end up with x on the bottom. So we're going to end up with this. Okay, so we've got c squared times x to the minus 1. That's what 1 over x is. X to the minus 1. That's just indices, right? So now we can differentiate this. What is it? Well, we leave the c squared alone. Okay, we're not bothered about that. We then we just treat it as a constant. We bring this power down, don't we? So this minus 1 goes out the front. This is the multiplier out the front. And then we reduce this power by 1. So it's going to go to x minus 2. So we end up with minus c squared over x squared. Right, okay. Well, that's the general expression of a gradient. Okay, so the gradient at any point. So we can basically look at our curve. Where is it? We can look at our rectangular hyperbola. Okay, and if we sub in, this is the equation of the tangent, will be given by what we've just found, minus c squared over x squared. Okay, so when we sub in our x coordinate, we can basically get what the actual gradient is. So we want the gradient at the point P. Okay, so we need to just sub in our x coordinate at the point P. So at x equals, what was our x coordinate of the point P? It was CT. So at x equals CT, so at our point P, we end up with the gradient being given by minus c squared over ct squared. I've just simply replaced x with ct. Do a little bit of simplification. We've still got the c squared on the top. Let's just square this bracket out. So it's ct times ct, so we're going to end up with c squared t squared. Okay, c squareds cancel. We're going to end up with minus 1 over t squared. So that is what the value of the gradient is at that point P. So we've got minus 1 over t squared. Okay, now we've got all the points, now we've got everything that we need to use our y minus y1 equals x times x, m times x minus x1. Sorry about that. M times x minus x1. Okay, because we know what our x1 and y1 is. Okay, the y's and x's stay the same. We know what our y1 and x1 is. Our x1 is our x coordinate of p, which is ct. And our y1 is c over t. And our m, we've just worked that out, is minus 1 over t squared. Okay. Now, what are we after? Well, we're after the form which we've given it in the question. So we're after this form here, which I've circled. T squared y plus x equals 2ct. So I'm just going to write that down to kind of see how we can manipulate this thing here to get it into t squared y plus x equals 2ct. So that's the thing which we're after. That's the thing which we want. So let's see what we can do here. There's a lot of t squareds and t's and things on the bottom, so I'm actually just going to multiply these fractions out, get rid of these fractions. There's no fractions in the final answer. Let's multiply these fractions. Good practice to get rid of fractions first anyway. So we've got this t squared. So if we multiply everything by t squared, we're going to get rid of this t squared, and we're also going to cancel this t out at the same time. Watch. So we've got t squared times y minus t squared, or I should write ct squared, write it in alphabetical order, ct squared over t equals minus, well, t squared over t squared is just 1, times x minus ct. Okay, so let's do that again. We don't have to multiply this by t squared, remember, because we've, the multiplier out the front, the multiplier of this thing is this 1 over t squared, which just goes to 1 when we multiply by t squared, and minus 1 when we go to t squared. Okay, so this t squared y remains the same. We can't do much with that. We can cancel t's off here, couldn't we? Because we've got t squared on the top and a t on the bottom. Just a lone t on the bottom. So we can cancel one of those t's off on the top, couldn't we? So break them apart, we end up with ct equals, let's expand this bracket out, so we end up with minus x. Careful here, it's a double negative, so minus times minus ct, so we've got plus ct here. Okay, the common mistake which people make is just getting the minus x and then forgetting about this plus ct. So t squared y, well the t squared y is in our final answer. That's, we've got that. We've also got the x. If we take the x over to the left hand side, we've got the x now. Okay, so we've now got that x. And then we've got ct on this side, and we've got minus ct on this side. So let's take this minus ct on this side, because there's no other terms on this left hand side. So if we take this ct on this side, we end up with ct plus ct. Right? And that, of course, is just 2ct. That's what we want. Okay, we've proved it. Where are the marks? Well, we get... let me just get up to here, because this is where our real working sort of starts. So we get 1 mark for recognising that dy by dx will give the gradient that we're after, so getting the correct method, okay? And we get another mark for getting the answer. Okay, so that's 2 marks there, basically, just knowing how to differentiate. We then get 1 mark for using the correct method with finding the equation of the straight line, the equation of the tangent, okay, and plugging them in correctly, plugging the numbers in correctly. And we again get 1 final mark for the answer. So there we are, 4 nice and easy marks. I have explained that in quite some detail, but hopefully that makes a little bit of sense now.